It started as a faint flicker on a cold July night in 2025, a glimmer so subtle that most telescopes ignored it. But the Atlas survey system in Chile didn't. Its algorithms caught something moving too fast, too far, and too freely to belong to our solar family. It wasn't a comet, not a rock, not anything tied to the sun. It was an intruder, the third one we've ever seen. We called it 3I Atlas, the third interstellar object to pass through our celestial neighborhood. And yet, from the very first readings, it refused to behave as expected. Where other visitors blazed unpredictably, this one seemed strangely deliberate in its stillness. Its coma, a cloud of gas and dust, began forming when it was still 5 to 6 astronomical units from the sun, farther than where Jupiter orbits. That shouldn't have happened. Not with so little heat. Not with that composition. Astronomers stared at its spectrum and found a signature dominated by carbon dioxide and cyanide compounds, but almost no water, an alien chemistry compared to comets born under our own star. Even the way it scattered light was bizarre. A negative polarization pattern, a kind of mirror inversion of what sunlight usually does when bouncing off cosmic dust. In its stillness, in its distant breath, 3I Atlas was whispering something about where it came from, and perhaps about what all interstellar wanderers are trying to tell us. When the Atlas team realized what they had caught, it was already racing through the outer regions of our solar system at nearly 37 miles per second, too swift for anything bound by the sun's gravity. It didn't orbit. It cut through space like a messenger that had already said goodbye to its home star eons ago. For scientists, this was déjà vu mixed with disbelief. After Oumuamua in 2017 and Borisov in 2019, astronomers knew these wanderers existed, but no one expected another so soon. The first detailed observations came from the Very Large Telescope in Chile and the Gemini North in Hawaii. As the data flowed in, something became clear. 3I Atlas was neither like Oumuamua nor Borisov. It glowed with an unsteady brightness that seemed to pulse irregularly, but not because it was spinning rapidly. Rather, it appeared to be shedding or reshaping itself. Photometric analysis hinted at possible fragmentation even before it reached its closest approach to the sun. That's almost unheard of. Most comets begin to break apart near perihelion, not before. Then came the shocker. The early outgassing, dominated by CO2, began when the object was still 5 astronomical units out. Water ice cannot sublimate at that distance. It's simply too cold. But carbon dioxide can. That alone told scientists this object had formed in a region of extreme cold, perhaps the outer disk of a different solar system, where sunlight never reached, and CO2 ice remained stable. Its anti-tail, faint but unmistakable, pointed toward the sun, a sign of dust particles large enough to resist solar radiation pressure. Combined with its negative polarization, this hinted at a highly compact, possibly carbon-rich surface, a material we've never seen behave this way on a comet. And then, there was the motion itself. The hyperbolic trajectory showed a peculiar eccentricity, slightly tighter than expected for an interstellar pass. Not enough to suggest deceleration, but enough to make scientists wonder whether we were observing a visitor that had been gravitationally altered by another star before crossing our path. For a moment, the astronomical community held its breath, because if that were true, if 3I Atlas was shaped by the pull of another sun before we found it, it might carry in its orbit the memory of 2 stellar systems, and buried in that trajectory, hidden in the mathematics of its speed and angle, could lie the first real clue to the shared architecture of planetary systems across the galaxy. A pattern that might show us we are not as unique as we think. When light from 3I Atlas reached our detectors, it wasn't just light. It was information written in the oldest language in the universe. Every wavelength, every faint dip in its spectrum told a story of what it was made of and where it had been. Using spectroscopic readings from JWST's NIR spec and ground-based follow-ups from VLT's 4S2 instrument, astronomers decoded something astonishing. This object's composition didn't match any comet in the solar system. Its reflection spectrum lacked the usual hydroxyl emission lines that come from water vapor. Instead, the dominant bands belonged to CO2, CN radicals, and faint signatures of carbon chain depletion, an absence of long-chain organic molecules that most comets here possess. This depletion pattern meant that 3I Atlas likely formed in an environment with intense cosmic radiation, where fragile organics were stripped away before the object was ever ejected from its home system. Even more revealing was the polarimetric anomaly. When sunlight reflects off dust, the orientation of the electric field, the polarization, usually follows predictable patterns, but 3I Atlas reversed it. A negative polarization at certain phase angles suggested a smooth, compact surface structure, with fine grains possibly fused by radiation over millions of years in interstellar space. The result? A cosmic fossil sealed by time and energy, carrying textures untouched since the birth of another star. And then came the data from the Hubble Space Telescope, which tracked its subtle flickers. The light curve revealed slow, irregular rotations, around 9 hours per spin, though the pattern was inconsistent. Something was affecting its motion, possibly jets of CO2 venting asymmetrically. Yet even these vents behaved differently. Instead of short bursts near perihelion, they persisted steadily as the comet approached 1.4 AU from the Sun, like a breath that never fully stopped. When astronomers modeled the scattering properties of its dust, they realized something else. The particle sizes were larger than expected, on the order of millimeters rather than microns. This suggested dense, cohesive material, the kind that doesn't easily fragment unless the object was already structurally unstable. It explained why small pieces might have started detaching months before its closest approach. What we were seeing wasn't a comet in the act of dying. It was a relic unraveling, exposing a chemistry and structure that had survived light years of radiation, silence, and gravitational exile. And as its light crossed our sensors for the first time in history, we began to sense not just where such visitors come from, but what kind of cosmic environments can shape them into the survivors they are. By late August 2025, the astronomical community was split. To some, 3I Atlas was simply another interstellar comet. Extraordinary, yes, but explainable. To others, it was the missing thread connecting Oumuamua and Borisov, the bridge between two anomalies that had never quite made sense together. The deeper the data went, the more this object refused to fit a category. At the European Southern Observatory, teams analyzed its spectral slope, a measure of how its brightness changes with wavelength, and found it flatter than expected for dust-rich comets. Flat slopes usually mean metallic or carbonized surfaces, not the fluffy, ice-dominated grains typical of a nucleus. Meanwhile, researchers at NASA's Goddard Space Flight Center argued that such composition implied not a fragile body, but something densely compacted, perhaps even partially sintered by cosmic rays over millions of years. Then came the orbital models. When plotted backward, its hyperbolic path pointed not to any specific star, but toward a galactic region near Lyra, a sector with several young stellar associations, but no single system matched its speed and angle of entry. That led to a radical idea. What if 3I Atlas wasn't ejected by a planet at all? What if it had been kicked free during the chaotic birth of its parent star, flung into the void by gravitational turbulence before any planets ever formed? That would make it older than most solar systems we know, a primordial shard from a protostellar disk. Some scientists countered that such an object should have been eroded by cosmic radiation long ago. Yet the polarization data and the large, cohesive dust grains suggested an opposite truth. Its skin had hardened, forming a shield that preserved its interior. Like a meteorite crust, but on an interstellar scale. The philosophical weight of this realization was heavy. If Oumuamua had shown us the variety of interstellar shapes and Borisov revealed their chemistry, then 3I Atlas was teaching us about their resilience, how far matter can travel and still tell a story. But something else troubled the data. Its brightness variation pattern didn't fully align with its rotation model. Some frames captured faint plumes directed sunward, as though the object were exhaling in rhythm with its spin. Others showed sudden dimming events, possibly caused by shadowed fragments drifting beside it. For a moment, astronomers wondered if we weren't watching a comet at all, but the slow disassembly of a body too old and too fragile to hold together any longer. And yet, what it left behind in those fragments might hold the most valuable clue of all. When 3I Atlas crossed the inner edge of its trajectory toward the sun, the first fragments began to drift away. At first, they appeared as faint flares, brief spikes in brightness, then silence. But high-resolution imaging from JWST's NIRCam and the Gemini North Observatory confirmed it. At least 3 distinct pieces had separated from the nucleus. Each fragment reflected light differently, as if composed of slightly varied materials, yet all shared the same spectral fingerprints, the CO2-rich, water-poor chemistry that made 3I Atlas so alien. The timing of the breakup was a mystery. At 1.8 astronomical units, the thermal stress should not have been enough to tear it apart. That distance is still colder than Mars's orbit. But the surface composition, dominated by volatile carbon compounds, may have created pockets of internal pressure, sealed beneath hardened crusts for millions of years. When solar heat finally reached those ancient chambers, they vented violently, splintering the body like a frozen lung collapsing from within. Each fragment then followed its own faintly divergent path, like pages torn from a cosmic diary. As they drifted, telescopes caught an extraordinary sight. The dust coma expanded asymmetrically, with one faint tail still pointing toward the sun, an anti-tail, caused by large, slow-moving grains that refused to be blown away by solar radiation pressure. This subtle geometry revealed the story of its death, the physics of disintegration written across sunlight and shadow. But those fragments carried more than a story of destruction. Their polarization behavior, still negative, still inverted, proved that even broken apart, the material retained its unique scattering properties. That meant whatever fused its dust was not just a surface effect, but a deep structural identity, an interstellar fingerprint embedded throughout the object. In studying those drifting pieces, scientists realized something profound. Each interstellar visitor we've seen so far, Oumuamua, Borisov, and now 3I Atlas, might represent different evolutionary stages of the same cosmic archetype. Oumuamua was likely a remnant stripped bare of volatiles, Borisov a young, active traveler, and Atlas, the aged wanderer, now unraveling after countless eons. This pattern hinted at an interstellar life cycle of matter, from volatile-rich birth to desiccated relic, repeating across the galaxy, linking planetary systems like beads on a cosmic chain. And if 3I Atlas truly embodied that final stage, then perhaps in its fragments we were witnessing the slow return of matter to the void, a death that feeds new beginnings. But one question remained. How many more of these ancient travelers are silently crossing our skies right now, unseen and unmeasured? By September 2025, as 3I Atlas moved closer to its perihelion at about 1.4 astronomical units, a strange rhythm began to emerge from the chaos. Telescopes around the world, from Pan-STARRS in Hawaii to Las Cumbres Observatory's global network, started comparing data, searching for consistency in its unpredictable light curve. Amid the noise, a quiet pattern appeared, a repeating fluctuation in brightness that seemed to correspond not only to rotation, but to cyclic outgassing aligned with solar angle. This wasn't random sublimation, it was synchronized. Each surge of CO2 release occurred at roughly the same heliocentric orientation, as if specific regions of the nucleus, ancient planes frozen in deep stasis, reactivated when facing the sun. That consistency told researchers that the surface wasn't uniformly active, but selectively alive, shaped by thermal memory from another star's light, long before it ever saw ours. When scientists simulated this behavior using thermophysical models originally designed for Borisov, the match was eerily close, except for one difference. The required thermal inertia was significantly higher. In simpler terms, the material of 3I Atlas absorbed and retained heat far longer than any comet we know. This meant it could hold volatile gases deeper within, protected by a crust dense enough to delay venting until the object warmed evenly throughout. That single property might explain why its outgassing began so far from the sun and continued with such resilience. But this discovery also raised an uncomfortable question. If such material exists, how common are objects like it drifting through interstellar space? Could there be thousands, maybe millions, of dormant 3I-like bodies crossing our solar system every century, unseen because they never outgas close enough to be noticed? Researchers at the SETI Institute and Harvard-Smithsonian Center for Astrophysics began running simulations, populating galactic models with 3I-like objects based on atlases, measured density and reflectivity. The results were staggering. Estimates suggested billions of interstellar fragments could exist per cubic parsec of the Milky Way. Silent wanderers, ejected debris of planetary formation spanning billions of years. In other words, interstellar objects might not be rare visitors. We might be surrounded by them, a hidden population, invisible until one happens to breathe near the warmth of our sun. And as 3I Atlas blazed faintly toward its closest pass, one thought unsettled astronomers worldwide. If we've already detected 3 in less than a decade, what happens when the next one arrives, larger, faster, and maybe carrying within it the record of a world that no longer exists. As 3I Atlas reached its perihelion in late October 2025, the debate over its true origin ignited into a quiet storm. Every telescope from JWST to the Subaru telescope had gathered months of continuous data, and now theorists face the task of reconstructing its journey through space, a voyage that may have begun hundreds of millions of years ago. Its composition, dominated by CO2 and cyanide with almost no water, pointed toward formation in a cold outer disk beyond the frost line of another star system. But that alone didn't explain the peculiar stability of its surface or the lack of fine dust. Some astronomers proposed that 3I Atlas originated from a binary star system where complex gravitational dynamics could fling icy planetesimals outward during the early stages of planet formation. If that were true, it would help explain its hyperbolic velocity, roughly 60 kilometers per second, consistent with the violent ejection energy of multi-star interactions. Others went further. They suggested that the object might come from the outer edge of a supernova-enriched molecular cloud, where radiation hardened its crust before it was ever gravitationally captured by a forming star. That would mean it carries within its atoms traces of heavy isotopes, cosmic fingerprints forged in the explosion of a dead sun. If future spectroscopy could confirm such isotopic anomalies, 3I Atlas would be more than an interstellar traveler. It would be a survivor of stellar death, a witness to the recycling of matter itself. Adding to the intrigue, new polarimetric models hinted that its negative polarization curve could be replicated only if its surface dust grains were partially amorphous silicates coated in carbon, a signature seen in dense interstellar clouds, but never before confirmed on a cometary body. It was, in a sense, a bridge between interstellar dust and planetary debris, the missing evolutionary step between raw cosmic material and the objects that seed new worlds. By mid-October, as 3I Atlas began its long exit from the inner solar system, fading into the glare of twilight, a strange realization took hold among the observing teams. We were not just looking at an object from another star system. We were looking at proof of cosmic continuity, that matter migrates across light years, binding star to star, system to system, in a chain of unbroken creation. And yet, as its fragments dimmed and data streams slowed, one haunting uncertainty remained suspended in every observatory's silence. If 3I Atlas truly carries the chemistry of another sun, then somewhere out there, a world once orbited that same light. Now, as 3I Atlas drifts back into the deep dark between stars, its trail of dust fades, but its meaning does not. What began as a dim spark in July 2025 has become one of the most profound reminders of what the cosmos is constantly doing, exchanging pieces of itself. Every interstellar object that crosses our skies is a letter written in the language of matter, carried across millions of years to remind us that nothing in the universe is truly isolated. From Oumuamua's silent shape to Borisov's fiery passage, and now 3I Atlas's gentle disintegration, we are beginning to see a continuum, a universal migration of worlds. These are not rare coincidences. They are evidence that the boundaries between star systems are porous, that gravity and time weave galaxies together as one vast, breathing ecosystem. In its final observations, before fading beyond 3AU, 3I Atlas left behind the quietest revelation of all, that even when shattered, it kept its chemical identity intact. It refused to vanish without telling us where it had come from. And perhaps that is its truest message, that endurance is the universe's first form of communication. Somewhere out there, fragments like it are still traveling, crossing the frozen gulfs between suns. Someday one of them will find us again, not as a mystery, but as an echo we finally understand. Do you believe these visitors are chance wanderers? Or are they the silent storytellers of the galaxy itself? Tell me below.